Hello and welcome to the Statistics and Mathematics Tutors course on Stochastic Processes. So today we're going to look at transition probability matrices. Okay, a convenient way of showing all the one-step transition probabilities is the matrix form. Okay, so over here we are looking at transitioning between the states that we have available. Okay, so let's say we have from state 0 to state m. So P00 means that we are transitioning from stage 0 to stage 0 itself. It's as in we are investing in this stock today and tomorrow we are investing in the same stock. That is what it means. So, or we can invest in this stock today and tomorrow we invest in another one. So, that is how this works, right? Note that the sum of each row of these transition probabilities should be equal to 1. Okay, and also their probability entries. So each of these probabilities should be bounded between 0 and 1 inclusive. So let's look at the Chapman-Kolmogorov equation. This says that, let's say we are interested in transitioning from state I to state J. Okay, we are moving from state I to state J in m plus n steps. Okay, so our goal is to move from state I to state J. This is our final destination. We are moving from state I to state J. But now the Chapman-Kolmogorov equation is saying that, okay, so if I, let's say state I is MTN stock and state J is actually go Apple stock. So I'm saying that, so in order to invest in to move from investing in MTN stock to that of Apple stock, let's find S&P 500 in the middle. That is the state K, so that we invest in MTN. Afterwards, we invest in that of what, S&P 500 before Apple comes to play. Okay, yes, that is what we call the Chapman-Kolmogorov equation. All right. So we are just finding some intermediate state between the final destination and the initial state. Okay. So as you can see here, as you can see here, sorry, as you can see here, we are moving from state I to state J in m plus n steps. So as you can see, any state at all we take K, which belongs to the state space. So we move from state I to state K in the first m steps. In the first m steps, then we pick our journey from state K to J in the last n steps, making the m plus what, n steps, and that is what we call what, the above equation is called the Chapman-Kolmogorov equation. Okay, we can also do the same thing to that of the two-step transition probabilities and so forth. This actually m steps. It's okay. That's very okay. Let's look at an example. As I said, if n is equal to 1, we have a one-step transition probability matrix. Okay, before really seeing this, let's look at this example. At an intersection, a working traffic light will go out of order the next day with probability 0.07, and an out of order traffic will be working the next day with probability 0.88. Okay, so let's take it that a working traffic is denoted as W, and that is equal to 1. It means that we are in state 1. So anytime a traffic is working, we are in state 1. And an out of order denoted O should be equal to state 0. So state 0 means that the traffic is out of order. Okay. So we said that a working traffic will go out of order the next day. The next day means that the time interval, this is a one-step transition probability. So a working traffic light will go out of order, meaning it was initially working. That is transitioning from state 1 of the traffic light working to being an out of order traffic light. So that means from state 1 to state 0 will give us a probability of what, 0.07. So that is what we see here. and the complement of that will be what? Remember I said that the row sum gives you 1. So meaning moving from state 1 to state what? 1 itself will give you what? The complement. That's 1 minus 0.07 and that's 0.93. Okay? And an out of order traffic will be working the next day with probability 0.88, meaning it is out of order, that is state 0, and now to be a working traffic light. So that is going to be from 0 to state 1. The probability of transitioning from state 0 to state 1 will be 0.88, and the complement will be from moving from state 0 to state 0, that's 0.12. Okay, great. Let's continue with our question. So yeah, so that is just that we've been able to know the transition probability matrix and its entries. Okay, yes, that's okay, that's okay. Yeah, so I think I've given you this already. Okay, yeah, you realize we use this expression to actually get the complement. So when you sum each row, you realize that it's going to be one. Okay, so let's look at the stock price example too. So at the end of a given day, the price of a stock is $1. So recorded by the stock line, given that the stock has gone up today, the probability that it will go up tomorrow is 0.7. So meaning up, the state of going up is actually 0, right? So going up today and the probability that it will go up tomorrow again. So up, meaning from state 0 to state 0 will give us 0.7, and the complement of that will be what? 0.3, as you can see. Let's proceed. So if the stock has gone down, the probability that it will go up. So let's say going down will give us 1. That means the state of going down is 1. So if it has gone down, meaning we are already down, and that's state 1, the probability that it will go up, that is 1 to 0, is 0.5. That is this. See? It's not confusing at all, very simple. Okay, so the complement of that will give us 0.5 as well. This is it. So this is a Markov chain, since the transition depends only on the stock going up or down. You see, it's just transitioning between up, down, just like that. Good. So transition probability matrix. So when we try to put it in a matrix form, you realize what we have here. So the stock going up is 0, like I said, and once you put it in the transition probability matrix, we beautifully get this. Okay, yes. So I'll come to look at these transition diagrams. Okay, you realize that this is a diagram that shows the movement we have between the states. So if you are moving, see, it just shows an arrow. It's a diagram. So somehow giving us a depicting a graphical representation of what is given in the transition probability matrix. Okay, yeah. So we'll look at these into detail maybe in a separate video, right? Good. So the two-step transition probability. If you want to know what happens next 2 months, okay, all this means that maybe in a month's time, the happening are those we've given as the one-step transition probability matrices. If you want to know the two-step, all you need to do is to square the one-step transition probability matrix, and we all know how to square matrices. So if you don't have a pre-recap on how to square matrices, maybe you try to do a revision on that. How to square it. When you square this matrix, you get this one. Squaring it means that you take this matrix and multiply by itself. Okay, and we beautifully get something like this. All right, yeah. So all the entries are nicely calculated over here, as you can see. Okay, yeah. So just review. Let me stand here for a while so that you see the computation. Then you try to do your matrix computation, and you get all these answers beautifully. All right. Yeah. So also let's look at the casino example. Suppose that a player leads with $1 and with each play of the game makes $1 with probability P and loses $1 with probability 1 minus P. Okay. You realize that when you either he loses or wins, the probability of winning is a complement of he not even winning, or he playing the game and not playing. They are complementary, P and 1 minus P. So the player either accumulates 3 $1 or goes broke. This game is actually a Markov chain. Okay, yeah, it can be seen as a Markov chain. We look at an example top there. So let's proceed and see what will happen. So now I think in this video we just stop here on this, and we've looked at several examples on transition probability matrices. Thank you so much for your time being. God bless you. See you in the next video where we look at transition diagram like I said. Okay, thank you. See you.